well, we will finish the Hard-Lefschetz theorem, and we will talk a little bit about the Hodge conjecture. Okay, so first of all, so let's finish the proof of Hard-Lefschetz theorem. So, wow. So proposition let X be a Kähler manifold then the Laplacian with respect to the differential D and the Lefschetz operator L commute. Okay, now I will use this other property that I stated in the last class that was about the commutator of I won't use it now, I will use it later. Okay, so let's compute it. Proof. Okay, so what you have to observe is that since nabla bar and Lefschetz, well, no, but since this guy, the adjoint of this guy is itself, and we call the adjoint of L by lambda, it is enough to show that the Laplacian commutes with lambda, right? Now we have to compute the commutator of this guy, and note that since the partial bar and the Lefschetz operator commute, this is because the omega, the one form associated to the Kähler metric is delta bar closed, right? So since these two guys commute, then lambda and the adjoint of partial bar also commutes. Right? Right? So now we can compute the commutator of I don't know if I will put it in this way. Lambda and the Laplacian is 2 times the commutator of lambda and the delta bar Laplacian, and we can compute this. This is 2 times. So this is the lambda partial bar star plus lambda partial bar star partial bar minus partial bar star lambda minus partial bar star partial bar lambda, right? And so since these two guys commute, this is the same as 2 times lambda partial bar star plus so maybe we can compute this at once. So this is the commutator of lambda with partial bar star, right? Partial bar. This is this minus this plus plus partial bar star, the commutator of lambda with partial bar. Right? This is this minus this. Right? And now we can use the identity that I saw yesterday, I mean the last class. And so this will be equal to, so I think it's 2i minus 2i. Minus 2i, partial bar, no, partial bar star, plus partial bar star, partial star. And this is the star of partial bar plus partial bar partial. And this is 0. Right? So that's the proof. Okay, so a corollary of this is that, so corollary, the Lefschetz operator sends harmonic forms into harmonic forms, right? So it induces a map from HPQ d of x to HP plus 1 Q plus 1 d of x. Right? Okay. So now the theorem. So this is the cohomological version of Hodge-Lefschetz theorem. So let X be a compact Kähler manifold of dimension n. Right? Then for every k between, okay, I will write it like this, then all r from hk, the Rham of x, to hk plus 2r, the Rham of x, is injective for all r equal to 0 up to n minus k. Right, so in particular for r equal to n minus k, we have an isomorphism. Right, this is n minus k, the Rham of x, to this is no, this is k n minus k to n minus k, the Rham of x. This is an isomorphism, right? And it is an isomorphism because it is injective and both spaces have the same dimension by Poincaré duality. Right? Okay, so this is Hodge-Lefschetz theorem, and we will prove it now using all the tools that we have developed before. And well, the property that I will use is this. Recall that the commutator of lambda with L, so it's lambda with L, L with lambda, is equal to k minus n, the identity in k forms. Okay, this is something that I didn't prove, in fact, but I told you that you can prove it if you prove it in Cn, and I left it as an exercise, and I didn't use it the last class, right? But now I will use it. Okay. Okay. So the proof. Okay, the proof is simple. So we proceed by induction. Induction on k plus r, that is between 0 and n, right? So for r equal to 0, there's nothing to prove. So now let's assume that k plus r is bigger than 0. Okay. So for, let's say, r bigger than 0, so we have the following identity. LR lambda is equal to LR minus 1 lambda plus I think it's like this, L lambda LR minus 1. Is that correct? LL. Yeah. Right, so now using this identity, we can compute, in fact, the commutator of LR with lambda, right, inductively. So what you will get is just that this is R times k minus n plus r minus 1 L r minus 1. Okay, this is super simple. Okay. So now using this, consider take any alpha. So I'm here, right? Any alpha such that LR of alpha is equal to 0. Right? They want to prove that it's 0. Okay. Okay. So so who is this? Okay. So we already know that if we apply this commutator to alpha, we will get the following equation, right? LR lambda alpha is equal to R times k minus n plus r minus 1 LR minus 1 alpha. Right? But by induction hypothesis, we know that LR minus 1 is injective. Right? So by induction hypothesis, we know that L lambda alpha is equal to R k minus n plus r minus 1 alpha. Right? And so we know that this number is non-zero because k plus r is less or equal than n, right? So this is negative, this number, right? So it's non-zero. In particular, we know that we can write alpha as L of something, L of beta, where beta is lambda alpha over r times k minus n plus r minus 1, right? Obviously. And so what this implies that L to the r plus 1 of beta is 0, right? But beta is what? Is lambda of alpha. Alpha is a k form. Lambda of alpha is a k minus 2 form, right? So this is a k minus 2 form plus, k minus 2 plus r plus 1 is k plus r minus 1. So again, by induction hypothesis, this implies that beta is 0. And so alpha is 0. Okay? That's the proof. Okay, so now I want to explain the relationship between this version of Hodge-Lefschetz theorem and the homological version that I introduced. I don't know which class, but maybe in the fifth class or something like that. Okay, so do you have questions? Everything clear? Okay, so well, the point that in order to relate this version of Hodge-Lefschetz theorem with the homological one, we need to look again at this Poincaré de Rham duality map, right? So again, so let X be a compact complex manifold of dimension n. Okay, so we know that we have this map that this is it takes the homology 2n minus k of x with let's say complex coefficients to the Rham cohomology group of x with complex coefficients. Okay, and so it takes some delta here, homological cycle, and leave it to some delta PD. It's a K format. They are related by the following equation, right? So intersection product of delta with some mu is equal to the integral of delta PD over mu for every mu in HK, K singular homology of X with complex coefficients. Right? This was the map that I introduced when I talk about an integral class or something like that. Do you remember when we talk about the Kodaira embedding theorem? We said that some one class was integral or rational if it were coming from something in the homology but with integers or rational coefficients, right? Via this duality map, isomorphism, right? Right? Okay, so we have this map. Okay, obviously, since this will be true for every delta and for every mu, right? So in particular, we can use the alternating of this intersection product, and we will get that this is equal to here a constant times the Poincaré dual of mu, the integral of the Poincaré dual of mu over delta, right? This constant is minus 1 to k, right? But it's a constant that depends only on k, on x, and on x, right? It's independent of the choice of delta and mu, right? Okay, there is something that I didn't mention, I think, but it's true. That in fact this Poincaré de Rham duality map it's well behaved with respect to the intersection product. So it can be shown that delta times I don't know, beta PD is equal to a constant. Here maybe 1, maybe something depending only on k and on x, times delta PD, wedge beta PD for every delta in, I don't know, k of c and every beta in j x complex coefficients. Okay? So in particular, what we have is that, in fact, what we will have here is that we have the following relation. So delta times mu, intersection product is equal to mu delta PD is equal to some constant delta mu PD is equal to some constant integral over x of delta PD wedge mu PD for every delta in H2n minus k and for every mu in HK. Right? I'm just using the Poincaré duality, I mean this isomorphism, for the intersection of delta times mu with the class of x. Right? Delta times mu times the class of the whole x is equal to the integral of x of the delta PD of delta times mu. That will be some constant times this wedge product. Right? Okay, so this is very important. Okay, so in fact, whenever we have this isomorphism, whenever we have a map coming from the homology at the homology level, even at the homology with integer coefficients, it induces a map in the Rham cohomology, right? And this is like is functorial, is covariant, right? So in particular, for x inside Pn, a smooth projective variety. So let x, let y, so equal to x intersected with some Pn minus 1 at the infinity, right? Well, it doesn't matter. Some Pn minus 1 is a smooth hyperplane section. Right, with respect to this same embedding, right? So we have y a smooth hyperplane section. So we want to compute this L. To show in some way that L is the dual, well, it's not the dual, it's the induced, map at the level of cohomology, and it comes from something here at the level of homology. Okay, so it will be induced by what? So we have the intersection map, right? Intersection map, that it's a map that goes from H to n minus k of x with integer coefficients intersect with y to h to n minus k minus 2 of x with integer coefficients. Right? This intersection map, what will induce in the Rham cohomology via this Poincaré-de-Rham isomorphism? So it induces a map that will be a map from hk the Rham of x to hk plus 2 the Rham of x. Let's call it phi. And by definition, phi of some delta PD will be equal to the intersection of delta with y PD. Right? For every delta here in h to n minus k, x with complex coefficients. Right? This is the map induced. And what is this? This is a number times delta PD, which the Poincaré dual of y. Okay, and what is the Poincaré dual of y? It should be, well, it's something times, it will be omega, the Fubini study metric of the projective space, ambient space, restricted to x. Right? Why is that? Why is that true? It's just because of y is the intersection, right? Right? And so we know that for every 2 cycle. So for every 2 cycle, we will have this identity, right? So if beta is any 2 cycle, I mean, we will have that the product of y with beta, it will be equal to the product of Pn minus 1 with beta, right? This is at the level of, this is in H star of x, let's say with complex coefficients, and this is at the level of H star of Pn with complex coefficients, right? And so again, by Poincaré duality, we know that the Poincaré dual of the hyperplane section is of the hyperplane in Pn. We compute it, and it's the Fubini study metric, right? I did that count in the class when I introduced the Fubini study metric. So we already know that this is equal to the integral over beta, I mean, times something of the Fubini study metric, right? And this will be something right? So it's this times a constant, maybe. Okay? So in particular, we conclude that this map is in fact the Lefschetz operator times some non-zero constant, right? So this phi is something times L. Right? So in particular, if we know if L is an isomorphism, then this map is an isomorphism, right? I mean, it won't be L, it will be L to the n minus k. It will be phi to the n minus k. But phi to the n minus k comes from this map, the composed map, the intersection map, n minus k times, right? So particular, if we have a tower of hyperplane sections, then this map, it goes from where to where, I don't remember, to n minus k of x with complex coefficients, right, that intersect with x n minus k to hk of x with complex coefficients. This map is an isomorphism. And since this map is obtained just by tensoring with C the following map of Q vector spaces, this map is also an isomorphism, right? And this is the version of Lefschetz theorem that I stated in homology, right? Okay. So with this, we have already proved all the Lefschetz theorems, almost all. There is one that I won't prove. In fact, I will ask you to prove it. Some of you. Someone. That is the Lefschetz 1-1 theorem. Okay. And now I will talk about a little bit about the Hodge conjecture, and I will just state the Lefschetz 1-1 theorem, and the proof will be left to the chosen one to talk about it. Okay, but it's not that hard. It's not too complicated. Well, with this, no, not yet. I think maybe in the next class we will close this chapter of L2 Hodge theory, and after that we will move to some more algebraic stuff. Okay. So a definition. So let X be a compact Kähler manifold of dimension n, but it doesn't matter. Compact Kähler manifold, we say that delta in H2n minus 2k x q. Okay, so here I will put respectively delta in H2n minus 2k x z. We say that this is a Hodge cycle. Respectively integral Hodge cycle. If it's Poincare dual, if delta PD it's inside the middle part of the Hodge decomposition of X. Okay, if delta PD is a KK class, right? So in particular, we know that, for example, in the projective space, I mean, a hyperplane section will always be a Hodge cycle, right? Because its Poincare dual is the Fubini study metric. That is a 1-1 form, right? So we say that omega in 2k the Rham of x is a Hodge class respectively integral Hodge class again if omega is delta PD for some Hodge cycle, right? In other words, if omega belongs to h2k of x with rational coefficients intersected with hkk of x, right? And here we're saying that omega is in h2k with integral coefficients, but here I'm looking at its image inside the cohomology with complex coefficients. Okay, Hodge cycle, Hodge class. Okay. So why are these cycles and classes important? So, well, first of all, before explaining that, I will put a proposition here. It's very simple. So let X be a compact Taylor manifold of dimension n. So then delta in h 2n minus 2k of x with integral coefficients is Hodge cycle if and only if the integral over delta of omega pq is equal to 0 for every omega pq PQ form, and for every P plus Q equal to 2n minus 2k and P different from Q, right? So again, the proof is just using this Poincaré de Rham isomorphism. So in one direction, so assume that delta is a Hodge cycle. So if delta PD it's in hkk of x, then the integral over the delta of omega pq is equal to something times the integral over x of, let's say, delta pq, delta PD, wedge omega pq, right? And since P plus Q is different, since P plus Q is 2n minus 2k and PQ is not n minus k, n minus k, whenever we do this wedge product, we will get 0, right? So this will be 0. And so this is 0, right? And conversely, conversely. So assume that we have a delta such that it's all these integrals are 0, right? So given such a delta, we know that delta PD is something, and we can write it as, let's say, eta 2k 0 plus eta 2k minus 1 1 blah 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 eta 0 2k, right? Where all these eta, let's say rs, belong to h rs of x in the Hodge decomposition, and r plus s is equal to 2k, right? This is Hodge decomposition. Right, so then we know that these integrals, right, the integral over delta of omega pq, they are all 0. And they will be equal to the integral over x of delta pd, wedge omega pq. And this will be equal to the integral over x of what? Of eta n minus p n minus q, wedge omega pq. Right, and this is 0 for every omega pq. Right? So since this is 0, again, since eta n minus p n minus q is an n minus p n minus q form, we know that then the integral over x of eta n minus p n minus q wedge omega is 0 for every omega. For every differential form, because it can be written in its Hodge decomposition, and all these parts are trivially 0 except the PQ1 that is 0 by assumption. Right, and this implies that this eta n minus p n minus q is 0 for every p plus q equal to 2n minus 2k and p different from q. Right, so this implies that delta pd is in fact only equal to eta kk. All the other parts vanish, and so it's inside HKK. So it's a Hodge cycle. Okay. Right. So this is a Hodge cycle. I mean, it's a cycle that where a lot of integrals are vanishing. Okay. Okay. So now I will introduce the algebraic cycles. So definition. Let X be a smooth projective variety of dimension n. And let Z inside X be a codimension K projective subvariety. Right? So there exists a homology class Z inside H 2n minus 2k of x with integer coefficients called its the fundamental class of Z, and it is given by the following relation. So it's the class such that the intersection product of this class with any alpha is equal to the integral over Z of alpha PD for every alpha 2K form, 2K cycle. Right? We know this guy exists, right? Since we can always integrate forms above algebraic subvarieties. And how do we do that? I mean, this is by definition the integral of alpha PD over the smooth part of Z, right? And this is well defined. Okay. Well, you can also define it in the homology side. I mean, using the intersection product. I mean, you can. What we're doing is that we're looking at the class defined by Z in the dual of the cohomology, right? This is the class induced by Z in the dual of the Rham cohomology, right? But we could have done it looking at the induced class of Z in the dual of the homology, using the intersection product. We can also define the intersection product of some cycle, homological cycle, with an algebraic subvariety, because you can always find a representative that is always intersecting Z in its smooth part, and also is intersecting it transversely in its smooth part. In both ways, you can define this homology class, the fundamental class of Z, right? Okay, but I don't will give too many details of this. Okay. So, definition. So we say that delta in H2n minus 2k x q respectively Z is an algebraic cycle if there exists some Z1 up to Zm contained in X, codimension K projective subvarieties and there exists some numbers n1 up to nm in Q respectively Z such that delta is equal to this sum, right? N1, the fundamental class of Z1 class, and M, fundamental class of Zm. Right? This is an algebraic cycle. Okay. And we have the following proposition. If X is a smooth projective variety, every algebraic cycle every integral algebraic cycle. Is a Hodge cycle. Okay, and what's the proof? So the proof is quite simple. After the other proposition, the only thing that we have to check is that the integrals vanish, right? So I mean by linearity we can assume that delta is supported in just one algebraic subvariety. And then we just need to check that these integrals are all 0, right? We have to compute these integrals, and we know that these integrals are these, right? Right, but when we restrict to this subvariety of the smooth points of Z, it's not too hard to see that. So for any x in Z smooth, so we know that the dimension of the tangent holomorphic space of Z is equal to the dimension of the anti-holomorphic tangent space of Z, and it's equal to the dimension of Z, right? That is n minus k, right? And so whenever we restrict this form, omega pq, at the point x, it will be, I mean, or p is bigger than n minus k, or q is bigger than n minus k, right? Since p plus q is 2n minus 2k, and p is different from q. One of the two of these guys is bigger than the half. And so one of these two guys is bigger than the dimension of x, of Z, right? So whenever you are restricting exterior form that over this complexified tangent space of Z, you will get 0, right? Because you will be alternating more vectors than that you are allowed, right? So this is 0. And so omega pq restricted to C smooth is identically 0, and so this integral is 0. Right. So every algebraic cycle is Hodge. And obviously, if that's true for an integral algebraic cycle, it will be also true for a rational algebraic cycle. I mean, with integer coefficients or rational coefficients. Okay. So, I mean, let's denote some notation. We denote Hodge XC, Hodge X, well, let's say here Q, Z, Hodge 2K, XQ, Hodge 2K, XZ, So this will be equal to h to k of xq intersected with hkk. This will be h to k xz intersected with hkk. So this is the spaces of, I will put this here, the spaces of, let's say, Hodge cycles, integral Hodge cycles, Hodge classes, integral Hodge class, respectively. And by h2n minus 2k x q Alge and h2n minus 2k xz Alge, the spaces of algebraic cycles. Okay, so what we proved is the following inclusion. So we have h2n minus 2k of xz Hodge is contained inside h2n minus 2k, I mean the Hodge 2n minus 2k xz, right? And so we also have it for rational coefficients, right? So the Hodge conjecture is just claiming that this inclusion is an inequality. Right, so conjecture Hodge conjecture is that so let X be a smooth projective variety of dimension n. Then for every k equal to 0 up to n, we have this equality. Right, this is Hodge conjecture. I mean, this is the Millennium Prize problem. And the same problem, the same conjecture for z instead of q is called integral Hodge conjecture. Okay, and it's known to be false. So the history is like this. The integral Hodge conjecture was proposed by Hodge. In 1941, And was this proved? By Atiyah and Hirzebruch. In 1962. And they proposed this current version of Hodge conjecture, which is open up to now, right? And so integral Hodge conjecture is known to be false. And now I will, I don't know what time is it. Let's see. I still have time. Okay, and well, now I will explain a little bit about what do we know about the Hodge conjecture, and with the theorems that we have already proved, and with also this Lefschetz 1-1 theorem that, in fact, is the one that inspired this conjecture. Okay, so theorem. This is Lefschetz 1-1. So Lefschetz 1-1 theorem says that, well, it says that integral Hodge conjecture is true for k equal to 1. Right? For codimension 1 subvarieties of x, we know that every Hodge cycle is supported in a sum of divisors. Right? This is Lefschetz 1-1 theorem. And it's true for integer coefficients, right? The integral Hodge conjecture. Right? This was proved by Lefschetz, and well, kind of the history of this thing is that, in fact, all these theorems that I proved, or that we have discussed about Lefschetz, they were all developed in one work, one very long work. I think that he spent like, I don't know, but it's like something like 11 years working in this thing. And his work was called l'analyse situs et la géométrie algébrique. And it was kind of an attempt to develop all the algebraic topology of algebraic varieties in the same spirit as Poincaré did when he developed the singular homology, singular cohomology, the fundamental group, and all this homotopy stuff in his work that is called el análisis situs. See, that's why he called his work el análisis situs et la géométrie algébrique. Okay. And the point is that Lefschetz proved a lot of theorems. In fact, this theorem, I think, it appears first in a work of Picard. Picard proved it, I think that in the case of surfaces, because he was motivated in understanding the topology and the geometry of surfaces. And the point is that after Lefschetz did all this big work, Hodge started to, its own research, trying to reprove all Lefschetz theorem, but with analytic tools. Hodge philosophy was that all the theorems that Lefschetz obtained were not were not due to the algebraic structure of the algebraic varieties. It was due of the analytic structure of the complex algebraic varieties. So that's why he started to study all these scalar manifolds and developed all this L2 Hodge theory in order to reprove a lot of theorems. In fact, the proof that I already gave to you today of Hartley-Lefschetz theorem is due to Hodge. I mean, and there is no other proof of this theorem. I mean, you cannot prove Hartley-Lefschetz theorem by geometric ways up to now. I mean, nobody has done that. The only proof is with these harmonic forms. And so, well, the only theorem that Hodge couldn't prove was this one, Lefschetz 1-1, and he was very impressed by this theorem, and he stated this conjecture. Okay, but he was motivated by this result. That's why he stated the integral Hodge conjecture and not the Hodge conjecture, right? Okay, so a remark. A remark is that, well, after we know Lefschetz 1-1 theorem, the integral Hodge conjecture is true for varieties of dimension less or equal than 2, right? I mean, for k equals 0 and k equal n, it's obvious, and so it's obviously true for curves, and for surfaces it will be true since we know the integral, I mean the Lefschetz 1-1 theorem that gives you for k equal to 1, right? So for surfaces, the integral Hodge conjecture is true. Okay, so we have here a corollary, let's say, well, a small proposition. Okay, a corollary. A corollary of Lefschetz 1-1 theorem is that a Hodge conjecture is true for k equal to n minus 1, right? So what's the proof? It's quite simple. So we have to prove that if we have we take any Hodge cycle in the second homology group, it has to be algebraic. That's what we have to prove, right? So let delta any Hodge cycle on the second homology group with rational coefficients, right? So by Hartley-Lefschetz theorem, we know that delta is equal to this, to some, I don't know, alpha times this x, which one is it? The h2, it's 2n minus 2, n minus 1, I think, n minus 2, right? Where this is the n minus 2 hyperplane section that you're taking inside X, right? For some alpha in H2n minus 2 X Q, right? So we have to check that alpha is a Hodge cycle also. And why is it a Hodge cycle? So since delta PD is equal to something times alpha PD, which this the Poincare dual of this, that will be just the Kähler form to the n minus 2, right? And we know that this is a Hodge cycle, right? So this is in h n minus 1, n minus 1 of x. So since this is a Hodge cycle, we know that omega to the n minus 2 is an n minus 2, n minus 2 form, right? So in particular, this alpha PD must lie in h11 of x, right? Right? It's because we're composing with the Lefschetz operator. Lefschetz operator is an isomorphism, right? And I already proved that it commutes with the Laplacian. So it gives you an isomorphism between h11 and hn minus 1, n minus 1, right? So this guy must be here in h11. And so alpha is Hodge, right? So alpha is Hodge, 2n minus 2 of xq, and this is equal to 2n minus 2 xq algebraic because of Lefschetz 1-1 theorem. And so we're done. I mean, if alpha is algebraic and this guy is obviously algebraic, the intersection is also algebraic. Right, so in particular, Hodge conjecture is true. It's true for threefolds. For projective varieties of dimension 3. It's also true. Okay, so what else can we say about the Hodge conjecture? In fact, not too much. Okay, integral Hodge conjecture. Fails for threefolds. And this was proved by Collar in the 1990. Okay, in the exercises, I will give you some examples of counterexamples to the integral Hodge conjecture. Okay. Okay. And so if we restrict ourselves to the case of hypersurfaces, x inside Pn plus 1, a smooth hypersurface, we already compute the its cohomology, its homology groups, right? We already know the following thing. We know that hk of x with integer coefficients is what? I mean, the middle part is a free thing, but we know that this is the class of x intersected with some p to the n plus 1 minus k times z for k equal to, so no, this is 2n minus 2k. So this is for k equal to 0 up to the integer part of n minus 2 minus n minus 1 over 2. We know this. We proved this using all these results that we conclude from Lefschetz hyperplane section theorem. And we know that this is some alpha k times z for k equal to the, I don't know how to call this, the roof of n plus 1 over 2 up to n, where this guy is a degree 1 cycle inside Pn plus 1. Right? Do you remember that we proved this? Right? Okay. And so in particular, we know that for hypersurfaces, so we have the following result, let's say. So for hypersurfaces, integral Hodge conjecture is true. For this case, right, for k between 0 and n minus 1 over 2. And also Hodge conjecture is true for these other cases, n plus 1 over 2 less or equal than k less or equal than n. This is by Leray-Lefschetz theorem. Right? You know that Leray-Lefschetz theorem is saying that the intersection map gives you an isomorphism between these groups and these other groups, right? The intersection map. So in particular, if this space, I mean the image of the intersection map will be also algebraic, because the intersection map takes algebraic cycle to algebraic cycle. But its image is not necessarily everything when we are looking at the integral coefficients, but when we look at it with rational coefficients, it will be surjective, right? So in particular, what we're saying is that this alpha k is, I mean, there exists some nk natural number such that this nk times alpha k is algebraic. Right? So a priori, this guy is not necessarily algebraic, but a multiple of it is algebraic. That's what we know. So in particular, Hodge conjecture will also be true for this other case, right? But it's not true, but integral Hodge conjecture is not true for these cases. May fail for this case. And this is exactly what Collard proved. I mean, Collard proved that integral Hodge conjecture fails for threefolds that are hypersurface in P4, right? So he proved it for n equal to 3, and he showed that the degree must be very high, right? And he proved that there are some threefolds inside P4 that they do not satisfy the integral Hodge conjecture. And how is that possible? It's only possible at this level, right? For k equal to 2, right? So it's a codimension 2 thing inside a threefold. It's a curve. He proved that for 2 cycles, there are 2 cycles that are Hodge with integral coefficients, but which are not algebraic. Some multiple of them will be algebraic, but not the cycle itself. And in the exercise, I will explain you more how are these examples constructed. Okay, integral Hodge conjecture fail. And so in particular, we have the following corollary. So corollary, let X be a smooth hypersurface. So if n is odd, if X is odd dimensional, then X satisfies Hodge conjecture. Every odd dimensional hypersurface satisfies Hodge conjecture. And if n is even, then X satisfies Hodge conjecture if and only if it is true for the middle homology, Hn of xq Hodge is equal to Hodge n of x. Right? So in order to verify Hodge conjecture for hypersurfaces, the only thing that we have to do is to restrict ourselves to the even dimensional hypersurfaces and just to check it in the middle homology. That's why it's important to know how to compute the homology of the middle part of the homology of a hypersurface, right? Because that will be the way to check, or to trying to check if this conjecture is true for a hypersurface. And even to prove the Hodge conjecture for hypersurface is a very big problem. It's quite difficult. Okay, so what time is it? I mean, just to tell you, well, the facts that we already know is that even for hypersurfaces, so for n equal to 4, right? It is true that, so we know that Hodge conjecture, we know that integral Hodge conjecture is true for cubic. And this was proved first over the rational number. It was proved by Zucker in the 1977, and it was proved. So this was over Q, the Hodge conjecture, and by Voisin, she proved in 2007 that it's true for over the integers. So this is something that is kind of recent, and well, you see its level, its degree of simplicity, right? So this conjecture it's quite open still. There are some other cases where this Hodge conjecture has been proved to be true. For instance, for certain classes of Fermat varieties, it's known to be true. But but in general, it's not too. There aren't even too many examples of varieties satisfying it. Right? To check it is hard, and always the hard part is in here. Well, both parts are hard. But this part is kind of as hard to compute as computing these integrals of a basis of the homology. But this part is much more difficult to understand. to produce algebraic subvarieties of an algebraic variety is something that in general is hard. And to check this, you have to produce a lot of algebraic varieties, enough algebraic varieties in order to complete this space, right? Well, do you have questions? For k less than n minus 1 over 2? No. It's you're saying in general, not for hypersurfaces. I'm not sure. I should check, but I'm not sure. But it might. It might be. I don't know. Yeah, it could happen. I mean, in general, it could happen. This is true just for hypersurfaces, right? And also, well, you can do the same thing for complete intersections, right? I mean, we can do almost the same thing for complete intersections. But for other varieties that are not complete intersections, I think that a priori it will be possible, but I don't know an example. I don't have anything in mind. Something that I didn't mention is that you could have the stated the Hodge conjecture not for algebraic varieties, right? We have everything that we need in order to state the Hodge conjecture for a compact Kähler manifold, right? In every compact Kähler manifold, you have this Hodge decomposition, so you can ask whether a cycle is Hodge. I mean, if this dual of this guy lies in the middle part of the Hodge decomposition or not. And in the algebraic side, you can replace it just by analytic subvarieties, right? Not necessarily. I mean, if you are in an algebraic variety, an analytic subvariety and an algebraic variety will be the same thing, right? So you can try to extend the Hodge conjecture for a bigger class, that is the class of compact Kähler manifold, and that's false. There are counterexamples to the Hodge conjecture in that setting, and also it's in the exercises.
For a complete intersection, X, how could you replace that constant? It could be n minus r over 2?
No, I think it's the same thing. It's just the middle part that you don't know. Yeah, in fact, when I tried to do this count in the class, I couldn't do it, so I just did it for the hypersurface case. I don't know if you remember, but in fact, it's true for I was just confused at the moment, but it's true for a hypersurface. I mean for a complete intersection, this thing. It's just applying the same hyperplane section theorem inductively. You will be able to do it. Maybe I should put it in the exercise too.